Alright, so in this video, I'm going to talk to you guys about ozone and how the IB really wants you to focus on ozone and connect it to many different types of chemistry that you have learned and that we will learn the rest of this year. So again, IB wants you to be able to connect chemistry to real life global problems, and this is a new concept, and they will be testing you on many different aspects of ozone. So one of the first things we're going to look at is how does ozone, which is O3 on the right side of your screen, how does it compare to oxygen on the left side? So we can see the structure of oxygen. It's a double bond. We can see that on the left hand side, like I said. On the right hand side, we have ozone, O3, so three oxygen atoms. And if you remember, we talked about ozone when we looked at bonding and how ozone actually forms a resonance structure. So therefore, you can see how we can draw the lowest structures of ozone both ways, and the double-sided arrow in the middle shows our resonance structure, and therefore the oxygen to oxygen bond is somewhere in between a single and a double bond. Now I want you to remember that because that's going to play an important role when we're comparing ozone to oxygen. So oxygen has that double bond. Ozone had that resonance structure and had a bond order of about 1.5, meaning that in order to break the oxygen bond, it's actually harder to do that than with ozone. Now, both of the bonds between oxygen and ozone can be broken by UV light, but light with a higher frequency is required to break oxygen. So because it has that double bond, it's going to take more energy, and more energy means a higher frequency. Now, we are going to be bringing back some equations that we learned last year where we looked at energy and related it to the frequency and the wavelength and the speed of light. So we have the energy of a photon equal to h times nu. Remember, h is Planck's constant, nu is the frequency. We're also going to incorporate wavelength, and we know that wavelength is related to the frequency by the equation nu equals c over lambda, where c is the speed of light. And when we substitute, we get this equation. So the energy of one photon of light is equal to Planck's constant times the speed of light divided by the wavelength. So this is nothing new, but it is something that we're going to have to remember, and we're going to be able to practice that. So here's a typical question that you might see. The bond energy in ozone is 363 kilojoules per mole. Calculate the wavelength of UV radiation needed to break this bond. So I'm giving you the answer. Okay, it takes 330 nanometers to break that bond of ozone. See if you can get there. Okay, see if you remember what to do. Again, we did this last year, so it's nothing new, but you're going to have to bring that back. Okay, so if you want to pause the video, practice, see if you can figure this out, and I am going to show you kind of the steps to get there. I'm actually going to show you two different ways to get to the answer. So we know we need 1 mole of photons to break 1 mole of bonds. Now the energy of a mole of photons is the energy of one photon multiplied by Avogadro's number. So you can see that in the first line, L, which is Avogadro's number, times the energy of a photon. The energy we're given is 363 kilojoules, so we can convert that to joules by multiplying by 1,000. In order to get the energy of one photon, we're going to divide by Avogadro's number. Okay, if you remember last year, we did something similar, but in reverse. When trying to find the ionization energy, had to multiply by Avogadro's number. In this case, we're given the energy, so we're going to go backwards. So once we know the energy for one photon, we can then use our equation on the previous two slides and rearrange it to solve for the wavelength. So wavelength is equal to hc over the energy. So we plug in what we know. Remember Planck's constant, 6.63 times 10 to the negative 34th. Speed of light, 3.0 times 10 to the 8th. And then in this last step, they took the answer from above and just flipped it because they are dividing by the energy. So remember, Planck's constant and the speed of light are both values given to you in the data booklet. When you plug all that into the calculator, cancel out units, you get 3.30 times 10 to the negative 7th meters. And we usually convert that to nanometers for our wavelength. So we're going to multiply by 1 times 10 to the 9th to get 330 nanometers. Now what this means is any radiation in the UV region with a wavelength smaller than 330 nanometers breaks the bond in ozone. Now remember, ozone has that double bond, so it's going to require a lot of energy, okay, in order to break it. So again, here's this problem from before, and I'm going to show you some other steps, a different method to get you the same answer. Okay, so I'm starting with the energy, 363 kilojoules per mole, dividing by Avogadro's number, 6.02 times 10 to the 23rd, to get me to kilojoules, and then I convert it to joules, and then plugging in to the equation for wavelength, you get the same answer, 3.30 times 10 to the negative 7th, and converting that to nanometers gets you to 330. Okay, so two processes, a little bit similar, some steps are different, but you get the same answer in the end. So with ozone, they could ask you to try and find how much energy is actually required to break a bond, and then ask you to take that energy and convert it into a wavelength. Okay, so make sure you understand these steps. Look back at your previous notes where we did some work similar to this when we learned atomic structure. Now, ozone is of great environmental concern because forming and more so the depletion of the ozone layer is of great concern for us. We want to make sure that our ozone layer is strong. So in the stratosphere, oxygen gas is broken down as seen here. So O2, when given a UV light with a wavelength less than 242 nanometers, is broken down into two oxygen atoms, okay, atomic oxygen. So the bonds break, that double bond breaks into oxygen. So on their own, they're free radicals. Hopefully you remember that dot means a free radical from your study of organic chemistry. They have unpaired electrons and are therefore very reactive. This is an exothermic reaction where then the free radical, one of the oxygen atoms, can combine with the other oxygen in the air to create ozone. Okay, in this step, we're actually going to create new bonds. However, we don't want ozone to constantly be increasing. So that UV light, with what you remember from the previous step, anything less than 330 nanometers will break that ozone. So if we have UV light from before, it also can be used to break down ozone, which we can see at the equation, second to last equation on the bottom, where ozone is breaking into an oxygen radical and oxygen gas. Okay, this ozone can also combine with a oxygen radical to create 2 moles of oxygen gas. Now, when it comes to ozone levels, and specifically we're talking about the stratosphere, which is a small amount, less than 10 parts per million, this stays at a constant level if the rate of formation of ozone is balanced by its rate of removal. This is known as a steady state. So we don't want the ozone to constantly be increasing from before. We want to keep it at a steady state, or it's not changing that much. This whole process is described by the Chapman cycle, which I'm about to show you on the next slide. Okay, so in this cycle we have oxygen, where the high energy UV light, again less than 242 nanometers, breaks it into two oxygen radicals. One of the radicals can combine with oxygen gas to create ozone, but the ozone can also revert back to the oxygen radical and oxygen gas. So we have step 2 and step 3. In step 4, ozone combines with the oxygen radical to create those 2 moles of oxygen gas. So this whole cycle keeps the steady amounts of ozone and oxygen, and it is really important because there is a lot of heat released. This is a lot of exothermic reactions going on, and so we don't want the ozone to be depleted, but we also don't want it to heat up. But this is an important cycle because UV light is being absorbed. The ozone is important so that the UV light from the sun doesn't reach the earth, and most of it is used to break bonds in the ozone layer. Alright, so now we're going to look at a couple of practice problems. You may want to try to practice these before, think about them, and then continue on with the video, and I'll show you the answers and kind of explain what's going on. So for number 39, we know that the concentration of ozone in the upper atmosphere is maintained by the following reactions. So we have a set of 3 different reactions with oxygen and ozone. The presence of chlorofluorocarbons, also known as CFCs, in the upper atmosphere has led to a reduction in ozone concentration. Identify the step which is exothermic in part A, and identify with reference to the bonding in oxygen and ozone the most endothermic step. So, for the answer for part A, step number 2 is exothermic, as we are forming new bonds. So in number 1 and number 3, it is endothermic. We are breaking oxygen in number 1, we are breaking ozone in number 3. But in number 2, we are creating a new bond when oxygen combines with the oxygen radical. So that is an exothermic step, forming bonds. For part B, the most endothermic step, you have to think about the bonding within oxygen and ozone. So we know oxygen has a double bond, ozone has a resonance structure with some delocalization, with a bonding intermediate between the double and single bonds. Therefore, the bond order is 1.5. Since the bonding in oxygen is stronger with that double bond, with a bond order of 2, it needs more energy and therefore would be considered more endothermic. Number 40, use section 11 of the IB data booklet to calculate the minimum wavelength of radiation needed to break the oxygen double bond in oxygen. So this is similar to the step before. We were calculating the energy required. So if we look in the data booklet, we can find that it takes 498 kilojoules per mole to break the oxygen double bond. So we can first convert that to joules by multiplying by 1,000. That is for 1 mole. We only need to consider 1 photon for the energy, so we're going to divide by Avogadro's number, 6.02 times 10 to the 23rd, and you can get 8.272 times 10 to the negative 19th joules. We are looking for wavelength, so we're going to use wavelength is equal to Planck's constant times the speed of light divided by the energy, which we just calculated before. So we can plug in our constants, plug in what we know, and we can calculate 241 nanometers. So any radiation in the UV region with a wavelength shorter than 241 nanometer breaks the oxygen double bond. So you can also compare that to the steps when we were looking at oxygen and ozone. It was about 242 nanometers. And that is the energy that is required to break the oxygen double bond. And last but not least, number 41, explain why ozone can be decomposed by light with a longer wavelength than that required to decompose oxygen. Okay, so we're looking at a longer wavelength. We know that if it's a longer wavelength, it's a shorter frequency, and if it's a shorter frequency, it's going to be lower, and that corresponds to a lower energy. So we know that the oxygen double bond is stronger than the 1.5 bond in ozone. Thus, less energy is required to dissociate ozone than oxygen. Longer wavelength radiation of lower energy is needed to dissociate ozone. So, not as much energy is needed to break that ozone bond.